2 more.
Wow. Are we going to do our last lecture, our advice lecture, research, what to do next?
Yeah.
Cool. Advising lecture.
Okay, ready?
I'm ready.
Welcome! EECS16A! Woo!
You see that? Remember question 2 of the midterm? Tell us a joke about circuits. That was one of them.
Circuits bras.
Yeah, circuit bra. Yeah.
Oh.
Is the alter?
Bra and kets. Okay, yeah, that's one of the drawings.
This is one of,
So
there
lovely.
were some good jokes. I am compiling them. The grading, by the way, is coming up.
Yeah. So midterm 2 grading is coming up. What else?
Labs.
Thanksgiving is this week.
Thanksgiving is this week.
Thank you for giving.
And then they come back from home, haircuts, new stuff. Yeah.
Oh.
Always. When the students go home, they come back with a nice haircut.
Okay.
Thanksgiving and spring break. I'm sure the parents make them do it.
Raise your hand if you watched the recorded lecture from last semester. Okay, you're good students. Thank you.
Half? Yeah. I read the notes though. You read the notes.
Okay, so last lecture, that instructor from the past has covered some material. One of them was trilateration, which relates to how, from measuring distances to different known location, you can figure out your position just by knowing those distances. And there, in that situation, it becomes a nonlinear set of equations, but there is this beautiful magic in those nonlinear equations such that they can become linear by looking at differences between several of those equations. Once it's linear, then you can put it in a linear system and solve it, but then you kind of like, instead of having 3 equations for solving 3 unknowns, you have basically 4 equations that are nonlinear. You linearize them, you get 3 equations, and then you're able to solve for 3 unknowns. We also showed you, how in a GPS system you actually don't need to carry with you an atomic clock that weighs, a few hundred kilograms, which is nice, because otherwise, your phones will be quite bulky, right? But then in your pocket, because you can solve for both position and time, in your pocket, you've got yourself an atomic clock. You can actually get the time up to 1 parts per billion accuracy. 1 parts per billion in your pocket, just because we have that amazing system that's called GPS. What's also, by the way, incredible about the system is the system, these things orbit at a, pretty fast velocities. There's also Earth gravity, and actually, because time is kept to such accuracy, the distortion of space-time due to Einstein's general theory of relativity, there's actually, you have to account for it. If you don't account for it, then GPS doesn't work. Okay? So that's pretty amazing as well, that we have to account for the general relativity in order to be able to get that. Anyway, what we then realize is like, oh, here's a situation where we have, let's say, 4 satellites. From 4 satellites, we got 4 equations that are nonlinear. We got 3 equations that are linear. We solve for, our position in space. Okay, what if we have 5, 6, 7, 8 satellites, and then we have all these measurements, and our measurements are noisy? What would happen then? How do we go about and find our location? We've got more equations than unknowns, which is possibly a better situation, but we got to the problem. So I just want to go back and kind of review a little bit of this, because I predict that some of you have not watched, and I don't want you to waste your time here in this class today, because we really, really appreciate you coming to class in person. Makes my enjoyment of teaching this much better, and hopefully this is a better experience for you. Okay, so overdetermined linear set of equations. I mean, we talked about that, kind of, but what does it really mean? Well, let's say I have two unknowns, x1 and x2, right? x1 and x2, and I make one measurement. One measurement means that I got some value, b1, out of a linear measurement, linear combination of those two vector elements. And what does really represent? So it's a two-dimensional space problem. My x1 and x2 are some position that I want to find, and they're somewhere in space. So there's some point that I want to find. But I have only one equation. What does that equation mean? How many solutions do I have, by the way? If I give you A11, I give you A12, you multiply and add, and then you get B1, what does that represent? A line, right? So why is this line? How many solutions there are for this equation? Infinite, because any point on a line would then be a solution for these two, for that one equation. Okay, so that defines a line. Okay, great. Then somebody comes with you and makes another measurement. Another measurement is another linear set of equations, and now that represents another line. Okay, and I'm going to draw that line. Now, hopefully, it's not the same line as we drawn before. If it was the same line as drawn before, then basically that measurements were dependent, and so I'm not going to get more information out of that. I'm just trying to repeat some of the things that we did in Module 1, right? So let's say this is the line that we got in this case. So where does my solution can lie? Where's my solution? The intersection between those two. So how many solutions do I have? I have one. It's unique solution. These are two independent equations, two unknowns. Therefore, I have a single unique solution. Do I always have a single unique solution when there's independent equations? When they're independent? Yes, I would always have a single unique solution. So this is the case where, we had like 3 satellites and we try to find our position. We get, reduce it to two equations, two unknown in a two-dimensional space, and this is what we get. So we know our position. But then your device is also listening to some other satellites, and you then pick another measurement, right? And hopefully you make another measurement, and that measurement can represent another line where your solution can lie on. And hopefully, that would intersect in the right place. And guess what it does? It does. And so we have a unique solution in this particular case. Wow, that's amazing. Okay? So even though we have 3 equations, 3 unknown, we have a unique solution. What does, by the way, mean? What does this, by the way, mean in this particular case? I have A times X equals B. A represent those 3 equations. X, the unknowns. B is our measured vector. What does it say about B when this is the case? What does it say? There's one solution, right, that satisfies all of them, right? So that solution where it is, it's like this one, that intersection. But what does it say?
You were too fast.
What?
He was going to tell you.
I was too fast?
Yeah.
Oh, you wanted to answer? Yeah, what does it say? When do I have a unique solution?
When B is in the column space of A.
When B is within the column space of A. Why? Because A times X means that I'm going to linearly combine the columns of A. And if B is within the column space of A, can be represented as a linear combination of the column space of the columns of A, that means that there is a solution that satisfied that. And that's great. Okay, so when B is in the span of the column space of A. Okay? But in reality, we might have noise, we might have interference. and all sorts of other stuff. And that may not be the case, that you have exactly those intersect at a single point. Every two equations may have a solution, but this may be a different solution for every set of two. So here's a more realistic scenario. X is actually where I am. But because of errors in my measurements, this is what I get. And the question is now, how do we find our position? I look at two equations, they intersect at one point. They intersect here. I look at another set of two, they intersect here. I look at another set of two, they intersect here. I don't know. I don't know where I am. Obviously, because of noise, there's uncertainty on my position. But the question is, what is the best, the closest solution that I can have to all these measurements? What do you do? If you watch the lectures, you would know. You do least squares, right? Least squares will try to minimize, like find a solution that is closest to all possible solutions, like to the best one, in some optimality criteria, which we're going to define. Okay, and that is the scenario that we're dealing with today when we talk about least squares. Does it ever come often? Does it ever come? Comma. Yes, often. Yeah, all the time. All the time. Least squares is one of the most used algorithms ever just to find solutions when you have inconsistent set of equations. Like your phones are computing least squares right now. I'm just doing least squares in my head, just because I like it. Okay? So in noise, there's actually no solution. In fact, what would happen is that you'll have, this B hat, like the contaminated B, really will not be within the span of the range of the columns of A. It would not be. So you can never reach it. There's just no linear combination of the columns of A that would reach this point. It's just impossible. So you want to find something that is close. Okay. So what did we do then last time? Well, what did we do last time? Here's kind of the situation. The fact is that we have measurements B, and we have a model that says AX should be equal to B. Okay? But the problem that we're having is that AX equal B don't have any solution. Like if you just solve Gaussian elimination, game but the algorithm, you would come up that there is no solution. And you would go like, Mickey, there is no solution. Well, that was module 1. Module 3, you go like, well, I can find maybe a solution that is optimal at some point. Like that would give me the closest possible one to some criteria. So the question is what to do. So what we want to do is we want to find some x hat. Some x, some value x hat, such that ax hat is the closest possible to the vector b. We cannot reach b, but we want to get as close as possible. What is the scenario? Well, the scenario is, let's say, you see this kind of flower lamp up here? You see this flower lamp up here? Okay. I can move in a two-dimensional space. Right? So I'm a linear combination of the columns of the matrix A. Where I am, it's a linear combination. So I'm trying to move anywhere in a two-dimensional space, but I really want to reach that flower thingy. Well, can you tell me what linear combination, what coordinate would be the closest one to that lamp? Well, I mean, like I'm just going to move. It's like, am I closest now?
Yeah. A little bit. No, to the front. Too much. So keep going straight.
Okay, and now okay, I can't get out of the plane because I don't have that vector to add, right? I can't get there, but that's the closest. Okay, so I decide that's the best. Okay? So there is some criteria of being close. And that is the geometry of the problems that we're going to deal right now, is that we can only move in the span of the columns of A, but we cannot reach B because it's outside of the span, but we can get as close as possible with some criteria. Okay? So I'm going to go quickly on this one because this, again, it's a review. So I have a situation. Here's a scalar problem, not even a two-dimensional. It's like a scalar problem. I've got two equations, one unknown. A1 times x equal B1. A2 times x equal B2. They're obviously inconsistent. Okay? I mean, they're an inconsistent set of equations. So one unknown, two equation. What does it really mean? What does it really mean? Where is the span of our solution? Well, I can only change x, right? That's what I'm changing. And I want to get as close as possible to this. So x is just a scaling of the vector a1, a2. Scaling of the vector a1 and a2, what does it give me? A line. Okay, a line that actually crosses the origin. Yeah? Because if x is equal 0, then crosses the origin, right? Okay? So it's some line. Okay? This is the vector A, and I can scale it. Okay? I can travel along this space, but B1 and B2 are somewhere else. So this is the span of A, but B1, but the vector B is actually this one. What I really want to find is I find the scaling of A such that I get as close as possible to B. Where on this line? Where on this line? Where on this line? Where? Well, okay. So what I want to do really is to find an optimal criteria. Oh, that's my keys. Thank you. My car keys. You find them?
Yeah. No, I found them.
Aww.
When you're jumping, probably still.
Oh, yeah. Shouldn't jump. Let's put them in a... Yeah, well, I could have been just stuck here all day and for the rest of the weekend. Okay, so what we really want to find is some x hat, some scaling, such that our error vector, ax hat minus b, is the smallest. Okay, we want to find the, what is the scaling of A such that I get as close as possible to B, and that norm of that error should be the smallest possible. Okay? And then what we did is we go like, oh, we tried this one, we tried this one, tried this one, this one, this one, this one. We look at the norm, and we found that the orthogonal projection, when there is a right angle between, when we go here, there's a right angle between E and A, then that is the closest solution, and we solved it using Pythagoras' theorem. Okay? So we want to calculate this orthogonal projection. So what is the point here? B hat that is closest to B, but it's within the span. Once I know what B hat is, I can also find x. Okay? By AX equals B hat. X hat equals B hat. Does that make sense? Any questions? Again, review. And I went through all this derivation. We said, oh, we know that E is orthogonal to B hat. Why is it orthogonal to B hat? Because in this case, the error has to be orthogonal to here. We proved that. So they are orthogonal. Then we said, oh, let's take the inner product between A and E. And we know that it's 0 because they're orthogonal. We derived something that came out of it, and we got to this equation. We found that x hat is the inner product between B and A divided by the norm of A squared. Okay, if you do not know what I'm talking about, watch the lecture again. Read the note. We're going to do it today again, but not just for one variable. We're going to do it for two variables. So it's going to be slightly more intense, but we'll be good. Okay, so this is what we got. So now we have equation for x hat. We know what x hat is. We then can find b hat, and this is b hat. Is the inner product between b and a divided by the norm of A, and it's in the direction of the vector A. Okay? That's a scalar. This is a vector. Okay? That's a scalar. X hat is a scalar. Multiplied by a vector, then you scale and find where it is the closest point. That is our geometry. Okay? So, orthogonal projections. We found an equation for orthogonal projections given vectors A and B. We say that the orthogonal projection of B onto A is, you can write it like this way, and it's A transpose B divided by the norm of A squared, which is also A transpose A, times A hat. This is a scalar. Can you see that this is a scalar? What's the top? A transpose B. That's an inner product, produces one number, scaling. Norm of A, also scalar. And that's in the direction of A hat. Okay, it has to be in the direction of A. Why? Because we're within the span of A. Right? We have to be there. Okay, so now I want to move into a multidimensional thing. Okay, it was easy to explain things in one dimension, but now I want to talk in multidimension. And this geometry appears over and over again, but now we're going to expand it. Okay? So I got 3 equations and 2 unknowns. 2 unknowns, actually that represent exactly the problem that I described before of me moving in this room and trying to reach this lamp. Okay? It's exactly the same thing, that geometry. So let's talk about that. We got 3 equations, A11, A12 times x1, x2 equals b1, A21 times x1 plus A22 times x2 equals b2, like this, like that, like this, like that, like this, like that. Okay, well, what does it really mean? Well, this is A, this is x, this is b, and I can also write A as the vector A1 and the vector A2, and I know that I can only reach points that are within the range of the columns of A, within the span of the columns of A, the range of the matrix A and the span of the columns of A. So it's just a linear combination between A1 and A2. Okay? So I can draw A1, and then I want to get as close as possible that, to B. Okay, so now I can draw A1. This is A1. What is A2? Some other thing. It's some other vector. It could be, again, what would happen if it was in the same, within the span of A1? Then A1 and A2 would be dependent, and that will just have a line. But let's say they're independent, and I can just draw A2. Okay. So now I can only reach points on a plane. It's like da 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 da. I can only stay in the plane. I cannot fly. Okay, so I'm staying within this plane. Da da na 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 na. Right? That's it. I can only stay. That's my span. Okay? I can only reach points on the plane. Okay, so this, I would say that plane is the column space of the matrix A. It's the span of the columns of A. All these the same things. What does it mean to not have a solution? B is in space, in the air. B is in the air, it's not in a plane. If B was in the plane, I would reach it, knock it down. Who wants to be B? Okay, I can reach it. But I also want to reach that flower, and I can't because there is no solution. I cannot reach. So this is the situation where there is no solution. No solution means that B is somewhere outside of that plane. And so B is not within the column space of the matrix A. And what I want to find some x hat, some solution, some x hat, such that I will get the smallest error. What will be x hat in this particular case? It's the coordinates of me, that would stand exactly underneath that light. Okay, that will be the solution. What will be the points? Well, the coordinate would be b hat, and the linear combination or whatever basis vector I have would be then x hat. Okay? All right. So what I want to do is I want to find x hat that has the smallest error. What is the error? Well, I don't know, I could pick x hat. Let's pick this point. Is that a good one? Well, let's take a look. Go from here to here. That's the error vector. Has a certain length. And I can say, sorry, this is not x hat. This is b hat. This is position b hat. And b hat would equal to some linear combination of a1 and a2, and that would be x hat. Okay, and I would reach this point. This is E. Is that the smallest possible error? No, it isn't. Okay, what about this one? Let's say now this is b hat, and is this the smallest possible error? No. What is the smallest possible error? Is I want to find kind of a right angle to that plane. Okay? So I want to find something which is the smallest possible error. So if I had a kind of perfectly flat plane, and I would have B, and if I would drop a ball, wherever that ball falls, that would be the point. If my plane was kind of elevated, that would not be true, right? It's not, gravity always goes down. But always think that, it's always right angle to that plane. Okay? So in that case, this would be B hat. Okay? And I would look at an orthogonal projection onto the column space of A. So I would like this to be 90 degrees. Does that make sense? Okay, orthogonal projection onto the column space of the matrix A, that's what I need to compute. That will give me B hat, that will give me X hat. That will be my solution. But now I need to find how to find those solutions. Okay, that's what I need to do. Folks, this is going to be like an aha moment in a second. Okay, we're getting to this like, oh my God, this is like a tattooing opportunity. You know what's a tattooing opportunity? It's like you see something and it goes like, oh my, I gotta tattoo this. Because like, just I want to remember that moment forever.
I'd totally go for it.
Yeah, you would?
I would.
Yeah, I can see that.
If it's really important.
Okay. So in order to develop that, let me just tell you a theorem. And here's a theorem. The theorem says, consider a matrix A, and let's say a vector y is in the column space of the matrix A. What is the example? The geometry is such that I have some, this is the, like, let's say this plane is the column space of A, spanned by A1 and A2, and y is somewhere within this plane. Okay? It's not in the direction of A1, not in the direction of A2, but you can find a linear combination that can reach y. Okay. What this theorem says, okay, so I've got A composed out of A1, A2, all the way to AN. So here's the theorem. If there is a vector Z such that the inner product between Z and AI equals 0 with all AIs, then the inner product between Z and Y is also 0. Okay? What does it say? Well, it says that if I have some vector z that is orthogonal to A1 and A2, it will also be orthogonal to y, okay, in this two-dimensional space. Does that make sense? Obviously, if it's just orthogonal to A1 but not to A2, that will not be true. But if I'm saying if there is a z such that is orthogonal to all AIs, then it will also be orthogonal to any linear combination of them. Let's see if that works. We're going to prove that. Proof. We know that y is some linear combination of A1, A2, all the way to AN. We know that. How do we know that? Well, we said it's in the column space of A. Okay? We need to show that z, inner product between z and y, is 0. How do we use the information? Well, we know this and we know this. We want to use both of them to show that this is equal 0. So how do we go about it? Yep. Yeah. Okay, let's see. So we want to show this, right? So let's just expand it. We know what y is. So let's just expand this. Okay? So we start with z inner product with y, but it's also z inner product with c1, a1, the linear combination of all those a's. Why can I do that? Well, I substituted. Instead of y, I picked this and moved it here. Now, because this is an inner product, I can say, oh, wait, this is therefore the inner product between z and c1a1. And it's also plus all the way to cn, z and an. Okay, so I can just expand that, that inner product. Woo! Wait a second. We know what Z transpose A1 is. What is Z transpose A1? Zero. What is Z transpose A2? What is Z transpose A5? What is Z transpose AN? So all of them are 0. Hence, I got C1 times 0 plus all the way to 0. Hence, the linear combination is also 0. So then, KQED, I proved it. Okay? So now I know that y is also orthogonal to z. Okay? We're going to use that. We're getting close. Oh, so excited. Yeah. I'm sorry, I was just like, having a hard time paying attention.
We know that z is orthogonal to every column vector of A. That means it's orthogonal to the column space of A.
Yeah, if z is orthogonal to any columns of A, then it's orthogonal to the column space of A. Yeah, that's exactly what we've shown. Okay. So we know that the norm of E is the norm of AX minus B. Why? Because that's how we define it. AX is B hat. We know the error vector is some x that we pick times A minus B. That's the error. We pick some x, we multiply by A, we look at the error, the difference, that's the error vector, and that's the norm of it. So the norm of E equals to that. In this particular case, it would be this one. What we want to find is the smallest error. Give me the x that has the smallest error. Okay? So the way I'm writing it, I'm saying, give me the x, argmin of x. We optimize for x such that this is the smallest. Okay? What are the variables? X. How we defined The cost function, that's also like the error, the size of the error, what's the norm of AX minus B? And we want to minimize that. That's an optimization. So this is A. AX is within the column space of A. Okay, it's a linear combination of that. And we want to find B hat, which is within the column space of A, that equal to AX hat, that minimizes this. So basically find the point that is an orthogonal projection. And now we start. Pay attention. Okay? I'm going to say E is B minus B hat. Is that right? Whatever we pick to be X, right? Whatever we pick, then AX will be B hat, so the error will be B minus B hat, just by definition. Okay. But I know that the closest one is the one that is orthogonal, right? So I know that E is orthogonal to the column, to every column of A. It's orthogonal to the column space of A, right? So it's orthogonal to any of the columns of A. So E is orthogonal to any of those. It's orthogonal to A1, it's orthogonal to A2, it's orthogonal to AN. Pythagoras theorem, based on that. Okay. That also means that AI, inner product with E, equals 0. Okay, that's what it means. From that, I wanted to find really what is X, right? That's kind of what I'm trying to show you. What is X? How do we find X? How do we find it? Where is X? I don't know where X. Right? That's our solution. So let's think about it for a second. So AI inner product with E equals 0. I'm building tension here. Pay attention. Pay attention. What is E? B minus B hat. Can I substitute? Okay, fine. I'll substitute. So it's AI inner product with B minus B hat. Now, we defined inner product for vectors. What is inner product for vectors? Can I just write it as A transpose B minus B hat? AI transpose B minus B hat, that should be equal to 0. Right? That's the definition of an inner product, Euclidean inner product. We're in the Euclidean space. Okay? Okay. That's great. Wait a second. That means that A1 transpose B minus B hat equals 0. That also means that A2 transpose B1 B hat, B minus B hat equals 0. That also means A3 transpose B minus B hat equals 0. Can I write it in matrix form? Like all of these are transpose times this equals 0, right? So I can maybe write, what is B minus B hat? It's a vector, right? So I can just write this vector. And what is AI transpose? Like it's 1 and 2 and 3 and 4. So I'm just going to use them as rows in a matrix. Can I write that? A1 transpose B minus B hat equals 0. Like this, like that, equals 0. And just to be more accurate, it's a 0 vector. A2 times times B minus B hat equals 0. Like this, like that, like this, like that, like this, like that. Can I write it the same way? Yeah? Raise your hand like this if you agree. Raise your hand like this if you kind of like, And raise your hand like this if you disagree. Do it, do it, do it. And if you do that, that means that you occupy like a state in an electron, like a spin.
Energy
but
state.
energy state, but that's not going to work for us. Okay. So that is very interesting. So I got these, and this is true, right? Like that's what we know. That's what we want. You know, we know that it is. But what is this matrix? Stare at matrix A. Has A1, A2 in the columns. Stare at this one. A1 transpose, A2 transpose, A3 transpose. What is this matrix? A transpose. A transpose. A. Whoa. Okay. We're getting there. So A transpose, so I can write like A transpose times this equals 0. Right? What is B hat? AX hat, right? So can I write that? A transpose B minus AX hat equals 0? How do we get there? We got there because we said that the error is orthogonal. Okay, that's what we said. The error is orthogonal. That's what we said. Okay, that's how we got here. Okay, let's expand it. I'm going to move a little bit faster. A transpose, so I'm open those brackets. Open those brackets. A transpose B minus A transpose AX equals 0. Is that okay? Just expand it. A transpose B minus A transpose AX equals 0. Can I take this to the other side and say A transpose AX equals A transpose B? Can I say that? A transpose AX equals A transpose B? I can. Just move it to the other side. Like if you just feel my heart rate right now, it's like 180
It's beautiful.
bits per hour.
What?
Heart rate, it's like 180 bits per 3 minutes. Anyway, A transpose AX minus this. Look, this is amazing. Okay, so now how do I solve this? Wait. What is this? What's the size of this matrix? A transpose X. A transpose A. What is this size? Is it long? Is it square? What is it? It's always square. It's always square. So now I've got a square matrix times a vector. And what is this? It's a vector. Wait. Before I had like a long times x equals a vector. I didn't know how to solve it. Now I've got a square matrix times a vector equals, right? Gaussian elimination. Not the game, but the algorithm. And when will we have a unique solution? Yeah.
There's a question there.
Is A transpose times AX hat the same as A transpose times A times X hat?
Yeah, there's distributivity, multiplication doesn't matter the order. The order doesn't matter. How you multiply things, matrices, right? Like you cannot exchange order, but the order of operation doesn't matter. I can compute this and then compute that, and I compute this and multiply by that. That doesn't matter. Thanks. Okay, so now I know how to solve. And when there is a unique solution, if A transpose A is invertible, columns are independent, has a non-trivial, has a trivial null space, determinant is not 0, all these things. Okay? Let's say that is the case. So if A is full rank, the rank is full, invertible and all that kind of stuff, then A transpose A is invertible. So x hat will be A transpose A minus 1 A transpose B. Can I write that? I'm just going to multiply by the inverse from the left side. Okay? The inverse of A transpose A, multiply by here, I'll get an I. I multiply by here, I get this.
Should I call 911?
That's a beautiful moment. We found x hat. That minimizes this. We started with orthogonal. Just say we want an orthogonal projection. This is what we got. And b hat, what is b hat? Is all this. What is b hat? This is x, so it's a times that, right? That will be b hat, right? Look at this beautiful symmetry. Do you see this beautiful symmetry? It's like A times A transpose A minus 1 A transpose. Look, it's just nice, beautiful, symmetric. That's the orthogonal projection. That's the solution for x hat. That's the best one. That's the closest. And that is the point where you're closest to the vector B. Folks, that's amazing. This is huge. Truly, this is one of the most useful equations you should ever use. And before that, there's a really excellent mnemonic for this one. Ready?
Yeah.
Ata a minus 1. Ata ba. Right? Don't forget it. Ata a minus 1. Ata ba. And if you have, instead of a b, you have a y, it's even better. It goes like, ata a minus 1. Ata. Yeah. Remember that one. Does actually compute. You know where these are? Errors from the past. I got A times X equals B. This is n by m. This is size n. What is, and this is size m. Okay? You do like this, like that, like this, like that, and so on and so forth, right? That works. Okay. What is A transpose A minus 1? That's a square matrix. What is A transpose? This one. What is B? What is X? You look at the sizes, it all computes nicely. Right? You look at this size, 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 perfect. They all compute. And this is the moment where it's really worth tattooing that equation on your arm. Right, Anna?
That's right. I forgot you had that picture of us.
That's right. Save this moment, because it is really, really one of the most useful things that you'll ever use. And I'm telling you, every time I got I want to regress some variable, this is what you use. You use that for regression. Okay, linear regression, whatever. This is what you'd be using. Oh, your question?
Yeah, I was wondering, because you use the Euclidean inner product with proof, does it only work with the Euclidean inner product, or if you had some other inner product defined, it's the same thing, because it's orthogonal equal to 0?
So, great question. We got this because we used the Euclidean inner product. What if we use a different version of an inner product? Well, the distance measure, E, would not be just a norm. It will be a norm derived from that new inner product, and we'll want to minimize that, and we'll have a slightly different equation. Okay? The equation will come out to be differently.
So you have to go through and prove this?
Yeah, you have to basically do, it's still orthogonal. You still want to find the orthogonal, but what is orthogonal with the new inner product? Absolutely. That's a great final question. Thank you. Fantastic. Good idea. Love it.
When was that?
Let's do some examples.
When was that?
What?
The picture.
Wow, that was when we had time.
We had time. We didn't have gray hair.
That's true.
So it's
I had
better.
more hair, actually.
You had more hair and not gray. And look
Wow.
at me, I didn't have gray hair either.
Well, maybe you colored it still.
No. I can see the streaks coming. It's gotta be 8 years.
A little bit of gray hair.
Yeah,
there
yeah.
coming. That's great.
Wow.
All right.
Yeah, let's keep going.
Examples. Now, we're going to start with simple examples. And again, for those who complained, I'm going to do simple examples because that's how we start. And then discussion, you have more complicated examples. Okay? Here's an example, just a very simple one. AX equal B. Okay? So, AX equal B, X, we're going to define X to be a scalar. And let's say now that we have two equations and one unknown. Okay? 2x equal 1, 1x equals 1. Obviously, don't agree. Right? 2x equal 1. What's the solution for 2x equal 1? 2x equal 1, what's the solution? 2x equal 1, what's the solution? Half. Half. 1x equal 1? 1. Obviously, they don't agree, right? That's what we're here. Okay, they don't agree. So 2x equal 1, 1x equal 1. Disagreement. Solve Gaussian elimination, not the game, but the algorithm. 2, 1, 1, 1. You get 1 half, 0 half, inconsistent. No solution. Game over, module 1. Come module 3. Let's find the least square. Let's find the closest. Okay? That's module 3. So in least squares, now folks, we have an equation. We have an equation, we just need to plug it in. We have A, we have B, atta A minus 1, atta ba, done. We got X hat. Super easy. Let's do it. What is atta A? A transpose A. So it's 2, 1 times 2, 1. Right? So 2, 1 times 2, 1. A transpose A. Do the calculation. What is it? Like this, like that. 5. That's right. Equal 5. What is atta A minus 1? What is the inverse of the matrix 5? What is the inverse of the matrix 5? 1/5. So, atta A minus 1 is 1/5. Okay. What is atta ba? Okay. So, atta ba is 2, 1 times 1, 1. Right? B is 1, 1. Atta is 2, 1. So, 5th, 2, 1 times 1, 1. Like this, like that. What do I get? 1/5 times 3, which is equal to 3 over 5. Beautiful. So the solution 3 over 5 minimizes the error between 2 times 3 over 5, 1 times 3 over 5, minus 1, 1. That's what it does. It minimizes that error. Yeah. Do we have a question? Yeah.
Is A transpose A, is it a matrix with 1 by 1?
In this case, it's a matrix 1 by 1 because it's a 1 by 2 times 2 by 1, right? It's a matrix 5.
Okay.
Yeah. Right now, it's a matrix 1 by 1, but it will be different when we go to more variables. Folks, this is great. Here's example 2. X equal B. And now, this is A. We have x1, x2, and this is B. Inconsistent set of equations. Perhaps. Is B within the range of A? I don't think so, because effectively this times, it gives me x2 is x2 equals 2 and x2 equals 3. Doesn't work. Okay? So if I'm going to go and write the equation, I would say, yeah, x1, like this, like that, x1 equal 1. Here, the equation is x2 equal 2, and here's x2 equals 3. Inconsistent. What is this? We want to do least squares. Well, it's inconsistent. We don't care. We know x hat equals ata a minus 1 ata ba. Done. Plug in. Solve. No problem. What is ata a? Minus 1? Well, you do the matrix A transpose times A, and then you compute the minus 1. So what is, this is A transpose A. If you multiply this by this one, you know what you get? I designed it to make it simple. It's a 2 by 2 matrix, right? It's a 2 by 2 matrix. And it's just 1, 0, 0, 2. Okay, you just do the calculation. It turns out to be diagonal. You can do this calculation like this, like that, like this, like that, like this, like that, 4 times. Okay? What is the inverse of this diagonal matrix? How do we compute the inverse of the diagonal matrix? No flip the diagonal. Invert the diagonal. That's it, done. Just invert the diagonal. That's the nice thing about diagonal matrices. And the nice thing about this simple example. So, the inverse of that is 1, 0, 0, half. Okay, that's the inverse. How do I know? If I multiply this one by this one, I get an identity. Okay, all right. Okay, so this is ata minus 1. Now I need to do ataba. This is ataba. Great. Do you know how to multiply these two? Do you know how to multiply these? Great. Let's do that. Okay? Like this, like that, like this, like that. I get 1 and 5. So this times 1 and 5. Now it's pretty easy. I get 1 and 2.5. Does it make sense? Well, obviously, if x1 says to be 1 and there is no contendant, then it should be 1 also after least squares. x2 had an issue, and we got the closest one, 2.5. It's the closest to both. Pretty cool, right? Automatically. Didn't have to think about it. No ad hoc. Optimal. Ata at minus 1, ataba, done. Yeah. Okay. Here's a very important problem for you folks. And the reason it's important because it affects your lives. This is a graph of real data collected by the number of time teaching EECS16A at the mean of the final exam. And you see that there is an interesting correlation between the more you teach it, the more you just make exam easier. Okay? All these folks have taught a lot. We didn't teach that much. So we want to come up with a model. And this data corresponds to, you know, the known stuff, right? Like we have Professor Waller taught X 1 times, and the mean of the exam that she has is Y1. Sahai taught X 2 times, and you get Y2. Oh, we're missing. It's Mickey and Anna, somewhere there, probably here. Okay, anyway, you've got all these points, right? So basically, you've got how many teaching, and then this, and you place those points. And now, we want to come up with a model. We want to come up with a model that represents this statistics. Find that correlation. So we want to simplify. This is just a scatter of points. We want to find some model to them. Okay, so what would be a good model? What would be a good model? A line, maybe a line. Why is it simple? How many parameters does a line have? Lines have 2 parameters, offset and slope. Okay? You can also do 1, but then it has to go through the origin. Right? So we want a line to fit to it. And let's say this may possibly be a good line. Right? Does that sound pretty good? Why does it sound to you good? Because you're doing least squares in your head. You're minimizing now all the distances. I mean, that's what you're doing in your head. Okay? You want to find something that is close to all those points, but cannot be on a, it cannot go through all those points. But it's close to all those points. And it has a model AX equal plus B. And that's our model. Okay, so the model is AX plus B. And I'm just going to stick Mickey and Anna over there. I missed it. And now the question is, what are A and B the best fit all those points in some optimality criteria? It's called regression, linear regression. Heard about that? Is it useful? Do you ever know how to do it? That's how you do it. Least squares. It's awesome. Well, we got all these points, but we want to fit it into the form of ata'a minus 1, ataba. That's what we want. To fit it into that form, then we know how to solve it. So least squares is easy. Machine learning is easy. The hard thing is actually taking a problem, understanding what are the variables, how to put them together, such that you can fit them in a form of A times X equals B. Then you can solve it. That is the key. That's engineering. And of course, finding the right model. Here we picked a linear one. Is that a good one? Maybe it is for this case. Maybe it isn't for some other cases. Okay, so let's do it. This is the matrix, and that's A. In this case, we're going to call P the unknown, not X. Why P? Because it's parameters A and B. So in that case, I guess I want to fill in, I don't know A, and I don't know B. These are unknowns. And I want to fill the values of those matrices and know what they are. So what's the first equation for Waller? It needs to fit this. Y equals AX plus B. That means that Y1 equals AX1 plus B. Is that right? Okay. Y1 equals AX1 plus B. What is, do we know X1? Do we know Y1? We don't know A and we don't know B. That's why A and B are here. But we know X1 and we know Y1. It's given. So how do I put stuff here in A and Y such that I will get Y1 equals A times X1 plus B? Well, the first element here multiplies A. What multiplies A? Not just X. In this particular case, I have X1 and Y1, right? Those are values, right? So I got x1 times A. And what multiplies B? So I'm just going to put a 1 here. Like this, like that, equals to y1. And now I used up this data point. Okay, done. I'm done with it. Let's go to Sahai, x2. That will be the second row of the matrix. Okay, now it's x2 and y2. Where do I put x2? x2 multiplies A. So I'm just going to put it below. This is x2. Like this, like that, times A. And what multiplies B? Still 1. And that equals to y2. You kind of see where it's going? What about x3? What about Miki and Anna? Yeah. What about Alon? What about Stojanovic? What about Renate, Cortade, Lou? All these will be rows in the matrix. And effectively, I will just fill them this way. So I've now created a matrix A, and I created a vector Y, and this is the unknown. So what is p hat? The optimal p hat. Atta, minus 1, atta, yeah! Solved. Equations. Look, the whole key was a linear model, 2 unknowns. Take the data, place it in the right place in the matrix. It creates matrix A, creates vector Y, and now solve using the equation. That's it. That's the magic. So the whole idea about this thing is how to find a good model and how to create matrix A and vector Y such that I can solve it with atta A minus 1, atta, yeah. Okay? That is the key. Okay? We're going to go through all of these. But can you see yourself now programming that in Python? Somebody gives you pairs of data. You go create a matrix A, just based on this. Create a vector Y and then just solve it. You can now compute linear regression on your own. Cool. That's cool. Come on, that's cool, right? That's cool. Now let's look at what is the error vector, though. Because the error vector is the one that we minimized. So we found a line. This is the line. And E is AP hat. What is AP hat? That's the line. Minus Y. Y are the points, right, in the y-axis. So what is each element of E? The elements of E are really the distances of these points from the line, right? AP minus Y, the Y component. These are the distances from these points on the line. And what we've done is we found a line such that the sum of squares of all those distances is minimized. The sum of squares of all of these is small. That's what we found. That's the interpretation. That's why it looked reasonable to you, because it's like, oh, there's no one that has actually too high of a distance, Like they all kind of fit nicely.
Mickey?
Yep.
For linear regression there, are we minimizing the error in the y direction or the orthogonal
No. You're
direction?
minimizing the error vector, and the error vector composed of what is ax minus y, right? Ax minus y. So you have a line, and the difference between the y component that you get for all these x's, then that is what you're trying to minimize. So, to be honest, every course that you go take a machine learning class, First thing you do, you solve least squares. Okay? Really, this ends up being, in many cases, the first thing that you'd be doing. Okay? You would basically do regression, some form of regression. In many, many cases, you just do some form of regression, which is quite interesting. But the thing is that not everything fits a line. And the question is, okay, what if it doesn't fit a line? Well, it's like maybe we can find out other models. Let's do that. Okay. I don't know if you've ever read XKCD. It's one of my favorite web comics. It's a good one. I love this one. Just picked a bunch of points and says, here are curve fitting methods and the message they send. The first one is linear. Hey, I did a regression. Okay, that's what it says. And this one, quadratic. I wanted a curved line, so I made one with math. Okay, that's a good one. And then this one, it goes like, well, okay, look, it's tapering off. I mean, you can just imagine whatever you want, right, in these points, which is true. It's like all these points, you can just fit whatever you want. So whether that represents reality, that's whether you picked a good model. And that's maybe your personality related. What would you be? Which one of these? I'm probably this one. Just jumping around. Okay. So let's talk about regression. And I think, we'll finish here. Okay, so least square is actually attributed to Gauss. He rediscovered least squares. It had been discovered a few times in history, forgotten, and then Gauss rediscovered it, which is kind of funny because we said that Gaussian elimination is actually not developed by Gauss, but then least squares does, but doesn't have any Gaussian in it, which is just funny how things are. But there was an interesting problem. Kepler was looking at, astronomers were looking at some anomaly in the orbit of planets, and they suspected that there is actually a planet that is another planet or another space body or something, dwarf planet actually, that is out there, and they wanted to figure out what its orbit is. And so they were able to look at this, and they tried to figure out, well, what is this orbiting? And they found this thing. It's called this dwarf planet is called Ceres. But then there were many days that there were basically clouds in the sky, and they weren't able to observe it. And so the idea is to figure out where it's going to be and what's actually its orbit. Okay. So imagine that these are the points of a two-dimensional orbit of the dwarf planet Ceres. And the question is, now is, what model would we pick for something orbiting something? If you believe in Newton, then it should be some ellipsoid, right? It should be some ellipsoid because that's what comes out from, mechanics. Okay, so the model should be some ellipsoid. How do we write an ellipsoid? Can we write it that way? ax squared plus by squared plus cxy plus dx plus ey equals 1. That is an ellipsoid. It's a quadratic, two-dimensional quadratic. And these are the points, and we want to find the coefficients, right? Actually, we know x and y coordinates, right? We know the x and y coordinates of these points. But we want to find A, B, C, D, E. Is this a linear equation or a nonlinear equation? Raise your hand if you think it's linear. Okay, raise your hand if you think it's nonlinear. Raise your 2 hands if you don't know. What is the known? We know those x's, like those x's are basically coordinates, x1, x2, x1, y1, x2, y2, x3, y3. So the x's and y's we know. We don't know A, B, C, D, E. They're in red. I'm trying to give you a hint. That's what we don't know. So even though x appears a square, these are actually scalars. There's x1, you just, when you want to put that in the equation, you put x1 squared, because that's physics. Okay, but x1 and x2 and x3, we know. y1, y2, y3, we know. We want to find A, B, and C. That would describe the best ellipsoid. So we can find series over there when it shows up. So then, once we find this, we can find this ellipsoid. Is this the best ellipsoid? Maybe, maybe not. Yeah. And the question is, to find that ellipsoid, is this a linear fit? It's a linear fit because the unknowns are just by themselves. You don't take them to the power, the unknowns. The knowns you take, but they're just constants. Okay, so it doesn't matter. Okay, so it is a linear fit. So the knowns are x1, y1, x2, y2, xn, yn. The unknowns are the vector p, which is a, b, c, d, e, transpose. And now, before we finish, just want to put that in a matrix so we can do the regression. Check this out. It's amazing. We're going to put this into, this is linear equation, so we're going to put it into AP times y, equals y. AP times y. AP equals y. That's what we're going to do. So here's the matrix A. This is the vector P. This is y. What is P? It's A, B, C, D, and E. And now, I want to take the point. First equation is the point x1 and y1. So, the points x1 and y1 needs to appear in A, P equals y. How does it appear? Well, A is multiplying by what? x1 squared. So I'm going to put x1 squared. B is multiplied by what? y1 squared. Okay. C is multiplied by what? x1, y1. D is multiplied by what? x1. And E is multiplied by what? y1. And when you do like this, like that, what do you get? 1. So the physics appears in the structure of the matrix A and the structure of the vector y. That's the physics of the model. Once you know the values that you kind of measured, you put them into the model by A, P times y, and then you just solve atta, minus 1. Atta, yeah! And you get the vector P. So you fill it. Can you now, given all those points, create matrix A in Python, C++, C, get your favorite language, Ada? Yeah.